Another application of exponential functions is the modeling of radioactive decaying elements. See, certain radioactive elements, radioactive isotopes, their instability causes them to actually lose mass as time goes by. So the information of the problem will usually tell you about an isotope's half-life. The half-life is the amount of time it takes for the material, the element or the isotope to lose half of its original mass. So here's a graphic example of what half-life kind of looks like. We're starting with a particular isotope that had an initial mass of 1,000 grams, and its half-life is 20 years. So we start with year 0, the time the isotope was first acquired, and the mass then was 1,000 grams. Well, if the half-life is 20 years, 20 years later, what that means is the mass is going to decay down to half that much, 500 grams. In another 20 years, from 20 years to 40 years, it'll go from 500 grams down to 250. And then 250 to 125 by the time you reach year 60. 125 grams to 62.5 grams by the time you reach year 80. So here are 4 half-life cycles of this isotope, and you see when you connect those data points with a continuous curve, it represents a decaying exponential function. An exponential function that's been reflected about the y-axis, so that the asymptotic effect is over on the positive side as opposed to the usual place on the negative side. So the model you can use to predict isotopes that have radioactive decay in their instability, you can use pretty much the same model we did for population growth. The only difference is this is representing exponential decay. If you have an initial mass measurement, then m sub 0 in this formula represents the initial mass that you've got. And notice you have e to the negative kt, pretty much the same formula where m represents an initial mass instead of an initial population. K represents the percent rate of decay for the isotope, percent per year or hour or day, depending on what the half-life is given as. Some isotopes are so unstable that they actually have a half-life measured in hours. Oh, and there's the typo again. I'm referring to K in the formula here. So K represents your percent rate of decay for the isotope, pretty much like the percent rate of growth for the population in the last couple of examples we did. T is the time in units, and again that depends on what the units for K happen to be. So again, if it's a half-life in years, percent per year for decay, then time will be measured in years. And then the m of t on the left represents the mass that it turns into in the future after you use this initial mass and you predict some kind of future mass amount that comes after year 0. Okay, so we're looking at an isotope of kryptonite. Kryptonite has a half-life of 8 days, and Lex Luthor has a plan on using a sample of kryptonite to kill off Superman. So we know that Lex currently has a 400 milligram, a pretty tiny chunk of kryptonite. What I want to do is, using the half-life of 8 days and that Lex's initial amount or mass of kryptonite is 400 milligrams, let's construct the mass model for this particular isotope. Okay, so again, m sub 0 represents the initial mass. The only data in the problem that we can use as an initial mass is the 400 milligram chunk. So I'm going to go ahead and take for granted that the initial mass we are using is 400 milligrams. And that will let us refine our model to this. That'll have to correspond to the time t equals 0. 400 for the initial mass times e to the negative kt. Then we need to use some other information to figure out the value of k itself. If the isotope has an 8-day half-life, then what that means is, again, here's your interpretation of half-life. If you have an 8-day half-life, that means I need to be able to plug in the value 8 days for my time and get an output of 200 milligrams, because you want to take half of that initial mass, and that's what the future mass will be after it's gone through one full half-life cycle. So I need to be able to plug 8 in for t in this function and get an output of 200 milligrams. So let's apply that here. M of 8, meaning days, according to our formula, that'll be 400 e to the negative k times 8, and I want to force that to equal the 200 milligrams, representing, the half mass that's left over after the half-life of 8 days. So, similar to finding the k value in the population, this generates an exponential equation that you have to solve to get your k value. Divide both sides by 400 to get that e exponent by itself. So e to the negative 8k equals, well, it'll always equal 1/2 whenever you're using the half-life, dividing 200 by 400. And then I want to take the natural log of both sides. So natural log of this equals natural log of 1/2. And again, there's your cancellation property that happens so much with these equations. Negative 8k will be the natural log of 1/2. So my value of k for this particular isotope for the mass model is going to be natural log of 1/2 divided by negative 8. Now this should actually give you a positive k value, because notice the negative sign is fixed in the model. You should not have a radioactive isotope's mass model with a positive exponent on E, because a positive exponent will guarantee the mass is growing. You need to guarantee the mass is decaying or going down as time goes by. So that negative needs to be preserved in the formula. So that means if I do this calculation, this should turn out to be a positive value for the letter k, but it defaults to being a negative in the exponent when I put it back into the model. So natural log of 1/2, divide that by negative 8, I'm getting a 0.08664 if I go to 5 digits after the decimal. 0.08664 for my k value. And now that I know k, I can finish the actual mass model. It says m of t equals 400. There's the initial mass that we start with. E to the negative, again, k is positive here, but it defaults to going back to negative when you put it back in the exponent. E to the negative 0.08664 T. And again, that'll be measuring mass in milligrams. Milligrams of kryptonite. Okay. So that is the mass model that we will use if we need to do any predictions for this particular kryptonite isotope. I think, if I'm not mistaken, yeah, there is a part B to this problem. Part B wants us to, it's on the next page. Part B says to use the mass model that you've got and, answer this question. 20 days from now, 20 days from the time Lex acquires the kryptonite, I'm assuming, 20 days from now, the mayor of Metropolis is giving Superman the key to the city as a token of appreciation for all the lives he has saved over the years. Lex wants to place his kryptonite chunk on the key to enact his nefarious plot. So, it's been found out that you need at least a 50 milligram piece of kryptonite to kill Superman instantly. Does he have enough kryptonite so that if 20 days from now, using this model, there'll be enough kryptonite left to have on the key to kill Superman? Well, so what I need to figure out is, what is the mass of this kryptonite chunk going to be 20 days from now? So I want to plug T equals 20. Again, I know it's in days because the half-life is in days. That means T for time is also going to be measured in days. Plug in T equals 20 days. So just evaluate M of 20 for your model function. Well, there's our model we just completed. So that'll look like 400 e to the negative 0.08664 times 20 for t. And let's see what this roughly leaves if we plug in 20 into our mass model. Okay, so 400 is the initial mass times e to the negative 0.08664 times 20 days later. So after 20 days, the mass will have decayed down to 70.7 milligrams. So apparently, if this is supposed to happen in 20 days after he acquires the piece of kryptonite, there is going to be enough in there to kill Superman. So, oh no, Superman may die. But, usually something happens. He ends up saving the day, and so hopefully maybe Lois Lane will kick in this time and save him. All right. I got one more example I want to show you, and then that'll wrap up all the radioactive decay modeling.